Okay, so what we just showed is that we can represent phasors in polar and rectangular form, right? We can write I of t in some format instead of I peak cosine of omega t plus, sorry, phi sub I. We can represent that as I equals I RMS at an angle of phi sub I, right? We could do that, and then we could convert that into some form A plus J B. Well, I'm here to tell you that it doesn't stop there. A lot of times what we're going to do is we're going to represent voltages and currents as exponentials, where we'll write it as IP e to the j theta or j phi, whatever you want to call that. Now I'm going to tell you that's not a super common method in power engineering. In communications technologies, though, when you start taking some of the classes on communications, representing voltages and currents in terms of exponentials is a much more common procedure. For good reason. We won't go into it here. You're just going to have to trust me that this is a common technique that's very applicable and helpful to our study of communication circuits, although it does show up in electric power systems every once in a while, so you do have to be kind of familiar with this information. So why can we do that? So the reason we can do it is something called Euler's equation, right? And it's an equation invented by, I believe, a French mathematician, Euler, and it is an equation that at its heart is trying to describe circular motion. And remember that. That's the point of the equation. A lot of times not pointed out in mathematical courses, is that Euler's equation, which states E to the j theta is equal to cosine of theta plus j times the sine of theta, right? So those are both theta. E to the j theta equals cosine theta plus j sine theta. So how does that equation represent circular motion? It's kind of confusing, right? Circular motion. The brilliance of Euler's equation lies in two parts. First is that he selected E, the natural number, and the second is that in the exponent he put the term j. So why are those so important? Let's start here. Adding the j term has the effect of rotating the value of the expression in the complex plane, and the use of E preserves the magnitude of the vector that's rotating. What does that mean? If we had picked values larger than E, this would have created a big spiral that got bigger and bigger and bigger. It would have graphed that. As theta went from 0 to infinity, we would have got a spiral that goes in this direction, right? And if we had chosen a value of E that was, or a value here that was smaller than E, you know, say 1 or something like that, it would have created a spiral that got smaller or tighter as it went. So this might make more sense to you if we plug in some sample values for, I wrote phi here, well, we're just substituting phi in for theta. So here I've got a table that I've written. We've got angles of phi ranging from 0 to 360, so you should recognize that as rotation around a circle, right? And if we plug 0 in, for example, to e to the j theta, if we plug 0 in for theta, we would just, on our calculators, we would type e to the j 0. And then what we're going to find out is that gives us the result, the rectangular result, 1 plus j 0, or 1 at an angle of 0 degrees. So now let's rotate by 45 degrees. Let's plug 45 into for theta here. And we plug that in, e to the j 45. That gives us 0.707 plus j 0.707, or in polar form, 1 at an angle of 45 degrees. And as we see, as we increase the angular rotation, we go from 1 at angle 45 to 1 at angle 90. This should actually say 1 at an angle of, no, it should say 1 at an angle of 135 degrees. So excuse me for that typo. Then we've got 1 at 180 degrees. We've got, there's a line somehow got missing here. 1 at negative 135 degrees, 1 at negative 90 degrees, 1 at negative 45, and 1 at 0. So what you'll see here is that as we're rotating, the magnitude of the result, of the function stays at 1, 1, 1, 1, 1, 1, and it goes from 0 to 45 to 90 to 135 to 180. That should be right here, right? Then we get negative 135, negative 90, negative 45, back to 0, right? And so, if we were to connect all those dots, we get and if we're good artists, I guess, we get a circle, right? We get that unit circle again. And so it's interesting. We plug in any value of theta for this, and the function that it's going to plot, if we were going to say x of theta equals, the function that it plots is a unit circle. That's amazing. So as we already know from the unit circle definition of sine and cosine that we've been using so far, a unit circle rotating counterclockwise gives rise to the sine and the cosine function. The cosine function, again, being the x component of the point rotating around the unit circle, and the sine function being the y component of that point. Since we're on the complex plane, y-axis values, remember, are preceded by the j operator, or imaginary terms, right? So these, since we're on the complex plane, these y values are going to be preceded by the j operator, and so you can see then how we got e to the j theta equals cosine of theta plus j sine theta, right? If we were to just draw some arbitrary vector with angle theta, the components of that point are going to be the x value and the y value, right? We know that that's the sine. We know that that's the cosine. So we end up with the e to the j theta is going to be equal to cosine theta plus j sine of theta. So pretty interesting result. We can kind of play a simple trick here too. We can think of the cosine again as the real part of this exponential function, right? This represents the projection on the x-axis, or the real part of it, and we can represent the sine function as the imaginary part, right? It's the y value, or the projection onto the imaginary axis. So a lot of times we will write that as we're going to say that the cosine of theta is equal to the real portion of e to the j theta Sorry, pen's acting a little wonky there, but the cosine of theta is equal to the real part of e to the j theta. That just comes from inverse of the Euler's identity. And the sine function, you can probably guess what's coming. The sine of theta is equal to the imaginary part of e to the j theta. So you may not have seen these mathematical terms yet. I'm not sure if they've come up in your calculus courses or not. The use of capital R lowercase e means the real part of whatever comes in the function. And the use of capital I lowercase m means the imaginary part of whatever comes in the function. Since we're using the cosine function to represent sinusoidal voltages, excuse me, we can kind of see the following relationships. We've got v of t equals cosine of omega t plus phi. Oh, sorry, V max. Should be a V max in there. Or V peak, whatever you want to call it. Cosine of omega t plus phi. So we can make a substitution, right? We're going to plug in V of t equals Vp, the real part, of e to the j theta. Well, in this case, remember, theta is just the argument of the cosine function here. The argument of the cosine function is omega t plus phi, so we need to change that into omega t plus phi, where again, we're just taking the argument of the cosine function and putting it in the exponential. And now I'm going to make a simple math simplification. Oh, I forgot my equal sign there. I'm going to just say V of t, the voltage is a function of time, is equal to the peak voltage times the real part of, and this is just math separation. Since I have a plus sign in the exponent right here, I can separate out those two quantities, right? So I can say e to the j omega t plus e to the j phi. So the next thing that we could do is we can move this peak voltage. It's a real quantity, right? It's totally real, so we can move it inside of the real operator. So because Vp, it's a peak voltage, it's going to just have, you know, a magnitude associated with it. It's not a complex number, right? It's just a scalar quantity. We can go ahead and move it inside. So we're going to go ahead and do that. And by doing that, we won't alter the mathematical results at all. I'm just going to clear the window. And the new thing I'm going to write, the new math expression is V of t is going to be equal to the real part of the peak voltage e to the j omega t plus e to the j phi. So again, the voltage as a function of time is equal to the real part of V peak times e to the j omega t. Oh, sorry, I wrote plus. That should be times. E to the j phi. So in this equation here, V peak e to the j phi is a complex number that carries the amplitude and the phase angle of the voltage sinusoid. V p e to the j phi. We say that's got the voltage magnitude. Remember, phi is the phase angle, so those two together, if I just pick those out, those carry the amplitude and phase information of the sinusoidal quantity. And by definition, this complex number right here is the phasor representation of the sinusoid. So I would say a lot of times it's written as the voltage. It's a phasor. It's got a magnitude and an angle, which means it's a vector quantity. It's got an arrow over it. It's defined as V peak, which is the max voltage, times e to the j phi. And we'll write this as capital P, curly braces, VM, or VP, excuse me, cosine of omega t plus phi. And the right-hand side of this here, the right-hand side, we read that as the phasor transform of. So this thing would say the phasor voltage V is defined as V peak times E raised to the J phi, which is the phasor transform of Vp cosine omega t plus phi. The frequent occurrence of the use of this has led to the shorthand that we use called the angle notation, where what we do is we just say V is equal to Vp e to the J phi is equal to Vp at an angle of phi. Right. So because we can represent the phasor voltage from the cosine function, this is the actual definition, and the angle form, which is the more common one, is really just this engineering shorthand. So if we were to use the rules for complex math, we could also write this phasor in terms of its rectangular form. So let's do that real fast. We could write V, the phasor, is equal to the max Vp cosine of phi plus J times Vp that's a sine, I don't know. So the phasor voltage can also be written as Vp cosine of phi plus J Vp sine of phi, right? So in this derivation, the peak values were used to define the phasor values. And in the introduction, you'll notice that the RMS value was used. So I've kind of shown it in two ways. Well, which is right? Well, technically, the use of the RMS value is called the RMS phasor, and the use of the peak value is called the peak phasor. So not too creative. If we use the RMS value, we call it the RMS phasor, and if we use the peak value, we call it the peak phasor. In power systems, we're almost always concerned about averages, almost always concerned, therefore, with the RMS value. And therefore, when we're talking about power systems, the term phasor and RMS phasor are often used interchangeably when voltages or currents are given as phasor values. I just want you to be aware that that is a notation in my class for power systems, that when we're talking about phasor voltages and currents, we're almost exclusively talking about RMS values. Ask for clarification from other faculty members. If they're putting phasor voltages out there and you're not sure if that's the peak value or the RMS value, it is important, and you need to make sure that you understand their notation. And that could vary between the different disciplines. Right? In power systems, though, we're concerned with the RMS phasors. So this may seem super complicated, but don't worry, it's actually not all that hard. Let's put it into practice, right? So let's work an example using the phasor notation. So we've got two trig functions here, and we want to write them in exponential, angular, and rectangular phasor form. So we want to take these cosine and sine functions and put them into their phasor forms. So what we're going to do first, you know what, I'm just actually going to rewrite them on this slide. So the V of t, the voltage as a function of time, is 170 cosine of 377 t minus 40 degrees volts. And we had another one, it's the current waveform, I of t, and we're going to say that that is equal to 10 sine of 1,000. And this one was plus 20 degrees. Clearly these are not related, right? We're analyzing these independently and we want to just put these in their phasor forms, right? So let's start with the voltage. Remember, the first thing that we want to do is convert that over to its RMS value. So to convert from peak to RMS, we're going to say the voltage phasor is equal to 170 degrees, or 170 volts, which is the peak value. We divide that by the square root of 2 to put into the RMS form. In this case, it's at an angle of negative 40 degrees. I can just infer that from the way that it's written, volts, right? So that's not too easy, not too hard. If I wanted to then write that in its complete format there, it's 120.21 at an angle negative 40 degrees volts. And colloquially, in electrical engineering, we would probably read that as 120.21 volts at an angle of negative 40 degrees. 120.21 at an angle, or 120.21 volts at an angle of negative 40 degrees is typically how we would say that. If I want to write that in its exponential form, remember it's just the RMS value e to the j phi. So in this case, it's going to be 120.21 e to the j. Phi is negative 40 degrees. Right? And that again is volts. So we would write that as 120.21 e to the minus j 40 degrees volts. And then I can use the rules for complex math to put this voltage phasor in terms of its rectangular and real components. Sorry, put it in rectangular form in terms of its real and imaginary components, and that's going to be equal to 92.086 minus j 77.27. Again, it's in volts. If you're not recalling how to go from polar form to rectangular form, I encourage you to rewatch the YouTube videos from Module 2, Part 3, where we go over that. Let's repeat the process then for the current waveform. The current phasor is going to be equal to the RMS value of the current, which was 10 divided by the square root of 2, so the peak over square root of 2 gives you RMS. And this one was going to be at an angle of negative 70 degrees. And this is going to be equal to 7.071 amps. At an angle of negative 70 degrees. If I were to write that in its exponential form, it's going to be 7.071 e to the minus j 70 degrees. And then if I were going to write that in rectangular form, it would be 2.48 or 2.418 minus j 6.645. Amps. Right. So if you're having any trouble with this exponential form, make sure that your calculator is configured in the correct setting for your angles, either radians or degrees, as appropriate. And then the last thing I want to point out on this example is regarding the calculation of the phasor function. You may be like, wait a minute, negative 70. Remember that the current phasor was defined, and the voltage phasor are defined in terms of cosine. In the problem statement, the instantaneous current, or sorry, the time variant current value was described as a sine function. So we had to phase shift from sine to cosine. Remember, we were at plus 20 degrees in the sine, but to go to the cosine, we had to subtract, right? Subtract 90. So when I'm going from the sine to the cosine, they're 90 degrees out of phase, right? So we had to subtract 90 degrees, 20 minus 90, negative 70, and the sine function is going to have this phase shift included in it. When we're using the phasor format, have to be in cosine waves.